Okay, welcome everybody. So today we're talking about chi-square tests. And so this seems like a lot, but if you look through the book, you'll notice that many of these sections are but one page, like 1.1 or 11.1 and 11.5 are both one page. So there's not really a ton here, and so we should be able to go through it fairly quickly. Okay, the first thing we need to know is this chi-square distribution. So have a look at section 1.1 and the chapter introduction and answer these questions and do this page. Fill in those blanks. This thing here I meant to be moved, so unfortunately that's a typo, and you'll see the same question later on. Yeah, you see the same question's been moved to here, where it makes a bit more sense. Okay, so let's start with what's called the goodness of fit test. And a goodness of fit, you have you have one population and one categorical variable, and you want to test and see whether that categorical variable is distributed according to some expected distribution. So that's some theoretical distribution. So the important thing to point out here is that it's one variable, it's one population and one categorical variable. Now that's important because it's going to contrast with the other tests that we're going to learn today. Okay, let's go ahead and so this is for you to read and to fill out. And then example 11.1, please just skim that, take a look at it. But I want to start with example 11.2. All right, so let's go ahead and do a chi-squared test for this one. And so again, I'm going to be assuming that you have looked at this and you have the test statistic for the chi-squared test. Okay, so employers want to know which days of the week employees are absent in a 5-day work week. Most employers would like to believe that employees are absent equally during this week. Suppose a random sample of 60 managers were asked on which day of the week they had the highest number of employee absences. The results were distributed as in the table below. For the population of employees, do the days for the highest number of absences occur with equal frequencies during a 5-day work week test at a 5% significance level. Okay, so this right here is observed data. It's an observed frequency table. And so generally with chi-square tests, what we're looking for is a categorical variable such as which day of the week are there the most absences. That is a categorical variable, right? Because the data is Monday, Tuesday, Wednesday, right? And so on. And so that's a categorical variable. And so we are now doing statistics on categorical variables. That's what section 11, chapter 11, is mainly about, is categorical variables. Chi-square test is indispensable in analyzing these things. Okay, so let's go ahead and this is our observed. Now, what would we expect? Right? What would we expect? We'd expect them to be distributed evenly. Okay, so you'll notice that all of these add up to 60. Now, if it was evenly distributed, how many would there be for each day? Well, wouldn't it be 12? There's 60 in 5 days. So our expected is 12 each day, right? And any one of those is total divided by number of categories. Now that's if it is evenly distributed, which is our assumption. Okay, great. So we've got the expected. Okay, so let's go ahead and start in with step 1. All right, the original claim. Okay, what's the original claim here? The results were distinguished for highest, let's see. Most employees would like to suppose that a random were asked which day they had the highest. Do the days for the highest number of absences occur with equal frequency? All right, so let's take that not as a question, let's turn it into a statement. Days for the highest number of absences do occur with equal frequency. So we're going to say, so the original claim here is that days have equal frequency. All right, that's my claim. And so, what does that look like? Well, that is chi-squared equals 0. Why am I writing chi-squared equals 0? Well, because chi-squared equals the sum of the observed minus expected squared over expected. Now, the difference between observed and this right here is a population, right? These are, of course, population parameters. So if the true observed minus the expected frequency, if this sum is 0, then that means that O matches E in every category, right? This is a sum over the categories. And so chi-squared equals 0 means observed, true observed, matches expected in every category. And the expected, in our case, is equal frequency. So that's why I'm saying chi-squared equals 0. Observed equals expected, which was equal frequency. Step 2, let me give myself some space here. Step 2, the opposite of the original claim, is much easier to write in math. That would be chi-squared is greater than 0. Remember, I'm not doing not equals to, because chi-squared will never be negative, as that comprehension question asked earlier. And what does this mean? It means that the days do not have equal frequency. All right, and that tells us that there's something, other than random sickness driving these absences. Okay, very good. All right, let's go to step 3, null hypothesis. Well, that's going to be the one that has equality, right? And so the alternative hypothesis is going to be chi-squared greater than 0. Now, all right, and so again, remember that this one right here is our original claim, so that means we are going to use the term reject in our step 8. From here, we see that this is going to be a right-tailed test. And as the book said, these chi-squared tests are almost always right-tailed. Okay, now it's time for step 4. What is the significance level they want? It's 0.05 is our alpha. All right, and now for the best part, this is step 5. Okay, so none of that, like that process, none of that was really very new to us. We've seen those first 4 steps. What is new, however, is going to be this is going to be this the computing the test statistic. Okay, so let me give you a few, let's see. So let's first of all see what we can do with copying and pasting this. There's that. Crop it way down here just to the numbers, and let's see how it does. Okay, can I crop it any smaller than that? No, I can't. Oh, that doesn't look promising. Come here, Command V. Oh, pretty good actually. All right, let's delete that. Delete that. Okay, and so here is my observed. Actually, let me move this down. This is my expected. Okay, now I've got to fix this a little bit. Actually, I think those numbers are probably just fine. Yeah, the only one that's off is this 17 here needs to be a 12, doesn't it? All right, so there it is. Okay, so what I'm going to do is I'm going to put now my O minus E squared over E. And now what is that for each one of these, right? We have to compute it for each one. So that's going to equal O minus E squared divided by E. Enter, there we go. And let's go ahead and Command C. I'm copying it. I'm selecting everything. I'm pasting, and it pastes in the formula. This one here, notice, is 0 because the observed matched the expected. And so that's 0. All these other ones, there was a discrepancy. See? All right, now chi-squared is equals the sum of these values. And that's it. That's our test statistic right there. Let's just go ahead and find the p-value while we're at it. Let's say I'll write step 5. There's my test statistic. Step 6 now. My p-value is going to be, actually, let me just put it down here. P-val is going to be equals chi-squared dot dis dot rt. And so this is going to, I'm going to put my chi-squared value right there, comma, degrees of freedom, that's k minus 1. That's however many categories there are minus 1. So in this case, that's going to be 4. Let's see now, why is it not? Well, anyway, enter. Okay, let me just, looks like it's got this weird word wrap. Let's see, home, there. Text wrap. There we go. Okay, so chi-squared dot dis dot rt degrees of freedom is 4. That's k minus 1. There were 5 categories, so minus 1 is 4. All right, just as you saw in, just as you read in the text. Okay, so that's our p-value. So I'm ready to screenshot this now. There you go. Copy and delete. paste. There we go. Okay, so my chi-squared test statistic is 3, and my step 6 p-value is 0.55. Now my data is not unlikely. Data is not unlikely. It's likely, assuming equal true distribution. Okay, step 7. Is alpha less than, is P less than alpha? Answer, no. So I'm going to fail to reject. And so step 8, therefore, is, since I'm failing to reject, there is insufficient evidence P equals 0.558 to reject. Remember, the original claim was in the null hypothesis. There's insufficient evidence to reject the claim that employees are absent each day with equal frequency. So there's no suggestion of any wrongdoing here in this case. It's all very even. So this right here is this difference that we observe right here on Monday. Look, it looks like Monday has more people that are absent, and Friday too, so it's around the weekend. That difference is not statistically significant, okay? It's not, you feel like you think you might have found something there, but actually it's not statistically significant. The chances of that happening just by random chance is 0.558. Okay, let's go ahead and take a look at the example 11.3 now. All right, so one study indicates that the number of streaming services that American families have is distributed. This is the given is have is distributed. And this is the given distribution for the American population, as shown below. A random sample of 600 families in the far western United States resulted in the observed frequencies in the second table at the 1% significance level. Does it appear that the distribution number of streaming services of the far west of far western United States families is different from the distribution from the American population as a whole? Okay, so this right here represents an expected value. These are percentages, right? So that's 10%, 16%, 55%, 11%, and 8%. And notice it adds up to, that all adds up, whoops, don't need to write that. That all adds up to 100%. Okay, and so if we wanted it to match, what would we expect if the 600 observations that we had followed that expected frequency? Well, this one here, the 0, would be 60, right? That's 10% of 600. See how that would be the expected frequency. This is not a relative frequency, this is a raw frequency. That would be the expected raw frequency if indeed 10% of the 600 had no streaming services. Okay, now the next one is going to be a little bit different. This is going to be 16 times 60, right? Because it's 16%. So 1.16 times 600. There we go. And that's going to end up being 96. For the expected. Okay, next is going to be 55 times 600, because 55%, or rather 0.55, right? And that is going to be, let's see, that would be 330. So that's a good chunk, over half, right? And that's what we wanted. And then next one is going to be 0.11 times 600, which is going to be 66. And then next we need 8. So 1.15 times, no, what am I doing? 0.08 times 600. There we go. And what's that going to be? 48. Okay, and you'll notice that if we add all of these up, we do indeed get our 600. So that's our expected frequency. So you see, we took this percentage that it should have been, we multiplied each of those percentages by the total, and we got our expected frequency. All right, let's go ahead and do the first steps. So step 1, original claim. Does it appear that the distribution of families is different? Okay, so is different. So the distribution, chi-squared tests are all about distributions. The distribution of Western family streaming service is different from national distribution. That's a little different. How am I going to write that? Chi-squared equals 0? No, chi-squared does not equal 0. So that's going to be greater than 0, because it can't be negative, so it'll be greater than 0. So there we go. So this is not equal. This is the same thing as chi-squared does not equal 0. Step 2, opposite of the original claim. Well, the opposite of not equaling 0 is going to be chi-squared equaling 0, and that is the distributions. And these are true, the true distribution of Western families. Matches. Okay, they match. Chi-squared equals 0. Observed and expected. The true observed matches the expected every single time. Okay, step 3, null hypothesis. This is going to be chi-squared equals 0. Alternative hypothesis is going to be the leftovers. That would be the alternative claim here. Okay, now notice that this is the original claim is in our alternative hypothesis, so our step 8 is going to say support. We're going to be able to support or fail to support the original claim. And this is, again, a right-tailed test. All right, step 4. Alpha equals, what's the significance level? 0.01, right? Right there. We know how to do that. Step 5, okay, it's time to put in my data. Because I want to use Excel. I want to leverage Excel in doing this. So I'm going to go ahead and, let's see, do I dare do the screenshot? These just have not been working out for me. Well, I mean, you know, they're okay. Let's just go like that there. Where's my, there it is. Copy and delete. I didn't really need to copy it, actually. Oh, maybe I don't. Let's just see what happens. Okay, so this one was absentees, or absences. And this one here is going to be streaming. All right, let's just see what happens if I paste. Ah, right, it added that to my clipboard. You know what? Well, no, let's see. So I'm going to go like that. There you go. Like this. See if I can get those expected as well. And I'm just going to go like that. Ooh. Copy. All right. There. There. Okay, use the optical character recognition. Thinks it's a phone. It thinks it's a phone number. Can't really. Command C. Can I copy that? All right, let's just put these in then. So this is going to be observed. And then over here will be expected. Okay, and observed is 66, 1119, 340, 60, and 15. And expected is going to be 60, 96, 330, 66, 48. All right, there we go. Now we need our O minus E squared divided by E. Oops. Divided by E equals, parenthesis, O minus expected squared divided by expected, enter. Okay, Command C, paste. There are those values, and so chi-squared is going to be the sum of these. There it is. Enter. 29. All right, that seems pretty big to me. So let's go ahead and do step 6. P-val is going to equals chi-squared dot dis dot rt. Again, it's an RT. It's always going to be a right-tailed test. Comma, degrees of freedom here. Any guesses? 1, 2, 3, 4, 5 categories. 5 minus 1 is 4. So it's going to be 4 again. Okay. There it is. All right, let me just go like this again. Let's see, select all, go here, take off word wrap. There. Now we can, there it is. There it is. Remember this one there was the sum. All right, very, very low. Let's go ahead and screenshot this. Command C, no. Copy and delete. Go back, paste. There we go. All right. So, chi-squared here equal 29.6464. Step 6. P value equal 5.7 times 10 to the negative 6. Just to show you guys what that is, that's 1, 2, 3, 4, 5, 5, 7, 7. So that is a very, very, very small number, right? And so step 7 is P less than alpha? The answer is yes. So we are going to reject that null. All right, see, so what this means is that my, the chances of me getting data, of me asking 600 people their streaming service, getting the number of streaming services from 600 people and getting a distribution like the one that I got right here is like 1 in a million, okay? So it's super rare, but my data should not have been rare. The reason it was rare is because I assumed that it followed this expected. Well, the conclusion here is that it can't have followed the expected. And so that's my step 8, is there is evidence. There is evidence to support the claim that Western, and I need to put in my evidence, P less than 0.001. Okay, I'm not going to put in this 10 to the negative 6 business. All we need to know is that it's less than 0.001. Western, let's see, there is evidence to support the claim that the Western distribution is different from national average. And that is statistically significant. Okay, we know that that these can't be the same. All right, very good. Okay, let's see, this one, let's make this one optional. I think we could go over this one in class, but you're not going to need to put it in for now. Let's go on to tests for independence. Okay, so go ahead and read this right here. All right, read that. And we're going to go ahead and start with an example. In a volunteer group, adults 21 and older volunteer from 1 to 9 hours each week to spend time with a disabled senior citizen. The program recruits among community college students, 4-year college students, and non-students. The table below is a sample of the adult volunteers and the number of hours they volunteered per week. All right, and so it doesn't say it here. I must have deleted the question. Or maybe, well, the thing that we would like to know is are the amount of hours independent of the type of volunteer, right? Are they independent or are they not? Okay, excellent. So let's go ahead and do our steps. Step 1, original claim. Turn that question into a statement. They are independent. Okay, so we're going to say they, the amount of hours is independent of the type of volunteer. Okay, now think about what that means in math. Chi-squared what? Is it going to be equals or is it going to be greater than 0? It's actually going to be equals. Independent is this expected. Independent is the same as the expected distribution that we are going to make. The one that you read about here, where you multiply the column total and the times the row total and divide by the grand total. So that's going to be that's the expected distribution. Whenever it's matches expected, so this right here is matches expected. All right, step 2, opposite of the original claim. Chi-squared is not equal to 0. It's bigger than it. And this is doesn't match expected, or is not independent. All right. Step 3, null hypothesis. Chi-squared equals 0, of course. Whenever it's equality, that's the null hypothesis. The alternative is the leftovers. This one right here is my original claim, so my step 8 is going to say reject. And then this is going to be right-tailed. Awesome. Step 4 didn't give a significance level, so let's go with alpha equals 0.05. Step 5. Okay, here we go. Off to Excel. But before we do, we need to get our numbers. So here I go. I'm going to screenshot. I'm going to do that. I'm going to come over here, and I'm going to try and grab these numbers right here. Really, it's just these I'm looking for. Oh, man. All right, let's try something else. Let's go like this. Take the whole table. I don't know if that copied. Command C. Okay, come down here. This is volunteers. Oh, look at that. Can I copy that? Command C. No. Let's try this again. Let's go like that. That didn't work. How about this? Okay. Oh, wait a minute. Oh, that's good. There we go. Copy. There we go. Nice. All right, great. Got it. Got the totals and everything. Okay, so this right here, guys, this is observed. All right, now what I'm going to do is I'm going to make expected over here. Okay, now equals, I need to do column total times row total divided by grand total. Okay, now I'm going to need to freeze. I'm going to want to autofill this, right? So I don't want the row to change on the column total. I don't want the row to change. So I'm going to put a $sign right there in front of the 37. I don't want the column to change when I move columns. So I'm going to freeze that one by putting a $sign in front of the F. Now for the grand total, I do not want either to change. So I'm going to put a $sign in front of both. Okay, look at that. Enter. And now let's Command C. Paste. There's my expected frequencies. It's the row total times the column total divided by the grand total for every single cell. Now watch what happens if I take the sum of these. Yeah, right? It always matches. Let me take the row sum here. $255, just like on the table. See, it still matches. But that's what it would be if it was expected. Okay, now I need to make one more table. This table here is going to be the O minus E squared divided by E table equals O minus E squared divided by E. I got to line up the cells in each table. Enter. Copy. There it is. Paste. There is my O minus E squared over E table. And now for my chi-squared, that is going to equal the sum of all of these. 12. There's my test statistic. And that's step 5. And now we'll do step 6. Equals chi-squared dot RT. Put that in. Now my degrees of freedom. That is going to be the number of columns, J, times the number of columns I minus 1, times the number of rows minus 1. And so since there's 3 columns and 3 rows, not counting the totals, that's going to be 2 times 2, which is 4. So we're going to have 4 degrees of freedom here. Press enter, and there's my p-value, and it's quite small. All right, let's go ahead and screenshot this. And there we go. Copy and delete. Come back over here. Paste. There we go. All right. Chi-squared equals 12.9909, and step 6 P equals 0.01132. Step 7 P is less than alpha, so that means reject that, null. Step 8, we're old hats at this, right? You've got, there is evidence to, now did I say I would say support or reject? Reject. there is evidence to reject the claim that number of hours is independent with volunteer type. Okay, great, we did it. So with that mathematical magic here, we were able to determine that these are not independent of each other. One of them favors more volunteerism than others do. Okay, there we go. All right, so there's that one. Let's see, I think this test for independence, let's make this one optional. You've already seen one of its type. Okay, let's go on a test for homogeneity. All right, so the test for homogeneity, I'll just give you the Reader's Digest version here. I really do want you to read the beginning section, and the section 1.11.4, and it isn't long, but basically the test for homogeneity deals with two populations and one categorical variable. Okay, that's the most important thing. And what you're doing is it's sort of like this test with two sample means. You don't exactly know what those means are. You're just trying to see if they're the same. It's the same, only in this case, you're testing whether the distributions are the same. Okay, so you've got two populations. Each one has its own distribution. And you want to know, do they actually match? Okay, now, notice that the test statistic here is exactly the same test statistic that you compute in the test for independence. Pretty much everything except for the interpretation is the same as the test for independence. The degrees of freedom, though, is... Okay, well, if you only have two populations, right, then you're just going to have the number of columns, right? And that's because the number of rows is going to equal 2. And 2 minus 1 is 1. So, anyway. All right. And then again, all values in the table must be greater than or equal to 5. That's not exactly true. It needs to be all values in the expected need to be greater than or equal to 5. If you have an observed quantity of frequency that's less than 5, that's okay, just so long as the expected is greater than or equal to 5. Okay, let's go ahead and take this example. So, do men and women college students have the same distribution of living arrangements? Use a level of significance of 0.5. So what is this? So the original claim is, do they have the same? So that is, do they agree with each other? Because if it's the same, then it's like independent. And so this right here is chi-squared equals 0. Okay, use that. Suppose that 250 randomly selected men college students and 300 randomly selected women college students were asked about their living arrangements. The results show the table. Do males and females have the same distribution of living arrangements? Okay, so that's really what we're going to test right there. It happens to be the same as what they said earlier, and that's fine. All right, let's go ahead. So, step 1, the original claim is men and women living arrangements are the same. And that corresponds to chi-squared equals 0. Step 2. The opposite of the original claim. And I'll just be a little short here. They are not the same. Meaning there is a difference between the expected, which you would expect if they were the same, and what the actual is and observed. Step 3, originally null hypothesis is going to be x squared equals 0, as always, because it needs to be equal. There we go. Okay, so this one here is the original claim. So that means we're going to say reject in step 8. This one here is right, indicates it is a right-tailed test. Step 4. I believe this was the 0.05 level of significance, so that's alpha equals 0.05. And now it's time for step 5. And let's grab our data here. Little screenshot. Go like this. You know what? Let's not go like that. Let's instead go like this. Yes. Yeah, I don't know how well that's going to work, but let's just see. Copy, go to, not Canvas, but Excel. Come down here, call this living. All right, let's paste. Oh, no, won't do. Let's go back to Notability, and let's screenshot. Let's grab this right here. Go like that. Let's see if we can get. It is just not recognizing that. Select all. There we go. Command C. Copy. Come to Excel. Paste. There you go. I think that worked just fine. 7284. Yeah, okay, that's fine. All right. Delete all that. Okay, so here are my 2 different populations. And each one of these are observed. This whole thing here is my observed table. And now what I need is my expected table. Okay, expected is going to equal. I need my column totals. Total equals sum. Enter. Command C. Command V equals sum. Enter. Drag. There it is. 550. Okay, and now it's time for the expected. And so this is going to equal column sum, or column times row divided by grand total. Okay, now let's see. Now it's the row total. I don't want the column to change, so I'll make that a G. Column total, I don't want the row to change, so I'll put a $sign in front of the 51, the row. For the grand total, I want neither of them to change, so I'm going to go like that. Enter. Okay, and let's go ahead and paste. Let's see, go 4 by 2, paste. And there they are. And I'll just quickly do these sums again. Yep. And the sums are always the same. $250, scroll that down, there it is, all the way to $350, all the way to $55. Okay, and now for my last table, I need O minus E squared divided by E. Enter. Here we go. Equals, parenthesis, O, expected, minus E squared divided by E. Enter. There we go. Command C, Command V. There's all of my values, each one for the, what is that? That's the relative square difference for each category, and now I'm going to sum those up. So there's going to be chi squared equals, and here we go, equals the sum. Enter. 10.1287. And now my p-value, this is what, this is step 6 we're getting into here. It's going to equal chi squared, as always, chi squared dot dis dot rt. Put in my test statistic. What's my degrees of freedom is number of columns minus 1. So that's going to be 3. Enter. There we go. There it is. Enter. 0.175. All right, let's go ahead and screenshot that. And there it is. There we go. We'll keep all of that. Copy and delete. Paste. All right, there is my test statistic and my p-value. So we've got chi squared equals what? 10.1287. Step 6, my p-value equals 0.017. Now let's do 18. Round it to the third decimal place. Step 7, now that thing is smaller. Well, now what's my significance level? 0.05. So P is smaller than alpha. So reject the null. Step 8, since I'm rejecting the null, there is evidence. Is evidence to, let's go back up here, reject, right? Because the original claim was that they are the same. There is evidence to reject the claim that the arrangements are the same. Okay, and then I keep on forgetting to put in my evidence here. And the confidence level even with 95% confidence. Okay, and that's my chi-squared test for homogeneity. Okay, then there's another one here, and this one here is optional. If you feel like you need another example, go right ahead and do that. If not, then you can move on. Okay, now this is a handy thing to read, so go ahead and take a look at that. Now we've got just one more test that we wanted to go over, and that's the test for a single variance. So I'll let you go ahead and read that, and let's go ahead and do example 11.10 right now. Now what I'm going to do is this final hypothesis test. So here we go. So with individual lines at its various windows, a post office finds that the standard deviation for normally distributed waiting times for customers on Friday afternoon is 7.2 minutes. The post office experiments with a single main waiting line and finds that for a random sample of 25 customers, the waiting time for customers have a standard deviation of 3.5 minutes. With a significance level of 5%, test the claim that a single line causes lower variation among waiting times for customers. Lower variation, yeah. Okay, so step 1, the original claim. Test the claim that a single line causes a lower variation. And so the single line was the experiment that they ran. And so that right there, so sigma, is so the variation of a single line is less than 7.2 minutes. Step 2, opposite of the original claim, the variation of a single line is not less than 7.2 minutes. All right, so here we go. So this is sigma less than 7.2. We are testing sigma here. This other one is sigma greater than or equal to 7.2. And so step 3, my null hypothesis, is going to be sigma equals 7.2. The alternative will be sigma less than 7.2. See, we know all of this stuff. Like, we can do this just fine. It's just the test statistics a little bit different. So they want alpha to equal 0.05 here. Now we do step 5, which is the test statistic. And if you look up here, you've got this test statistic that we want to use. All right, so this is going to be chi-squared. So chi-squared equals n minus 1 times s squared over sigma squared. And so that is going to be, what's n? 25 minus 1 is 24. What's s? 3.5. So let's square that. What's sigma? Well, the null hypothesis gives us that, 7.2 squared. All right, and so we can compute that using a calculator, or we could use Excel. Let's go ahead and use Excel. call this lines. And so this is chi squared equals, equals 24 times 3.5 squared divided by 7.2 squared. Let me just go back. Yeah, that looks fine. Enter 5.6. Let's find the p-value. Equals chi squared dot dis dot rt. Well, actually, what is this? This looks like it's a left tail test. So it's not going to be RT, it's going to be the usual one, which is not without the RT. All right, so we need our X value there, our degrees of freedom. Do we recall what that is? Look up here, n minus 1. And notice what it says, a test for a single variance may be right-tailed, left-tailed, or two-tailed. So that's going to be 24 is going to be our degrees of freedom, comma 1. All right, because we want the area to the left. So we'll do 1, enter, and it's really very, very small. All right, let's go ahead and screenshot that tiny little bit. There we go. That. Copy and delete. Come here. Paste. .671. Step 6. P equals, yeah, very small number, 4.21 times 10 to the negative 5th. Step 7. P is less than alpha, RTN. Right, reject the null. Step 8. There is always evidence when we reject the null. There is evidence to let's see now. What's the null hypothesis? The original claim is in the alternative. And so we are going to use the term support. And this right here was a left-tailed test. There we go. There is evidence to support the claim that the single line decreases variation. It wasn't just a fluke, it was statistically significant because my data was super rare if I assumed that there was no difference. All right, everybody. So go ahead and, yeah, that does it for us. Okay, have a great day, and we'll see you in class.